Now that we've written Maxwell's equations in tensor formalism, we can start looking at other quantities now. And one of them is the Minkowski force. So if you remember, the Lorentz force was F is Q E plus V cross B. So the Minkowski force, one would think, would involve Q, it would involve the fields, and it would involve the velocity V. And so the Minkowski force we'll write with a K, and we'll write it in tensor notation, K mu, and we'll have the charge Q, we'll have a velocity term, nu, eta nu, and then we'll dot product that with the field tensor, like so. So this is our new force equation, which has all the pieces, but all those pieces are now relativistic, and they span over the four dimensions. So if we kind of look at this, we could take a look at when mu is equal to 1, and so in that case what we would have is k, one component, q, eta nu, f1 nu. So now the nu is a dummy index where we can apply the dot product. And so K1 is Q eta 0 F1 0 plus Q eta 1 F1 1 plus Q eta 2 F1 2 plus Q eta 3 F1 3. And so now if we put all the terms in, we would have, I could factor out a Q, and I would have minus c over the square root of 1 minus u over c squared. So that's eta 0. So f1 0 would be minus ex over c. f11 is 0 plus uy over gamma, times gamma. Okay, so that's eta 2 is the y component of the velocity times the z component of the magnetic field plus uz 1 minus u over c quantity squared minus by. Okay, so then if we can cancel one of the c's, we can cancel the minus sign, we can factor out the 1 over the square root. So that's just gamma, so I'll call that gamma q, and we're left with ex plus uy bz minus uz by. Okay, this right here is the velocity crossed into the magnetic field, the x component of that. And so what we're left with is gamma q, the x component of the electric field, plus the x component of the cross product of the velocity with the... And so if I look at this, this right here, I could call my relativistic correction to the charge. And in the end, what we have is something which looks like a Lorentz force. And so mu equal to 2 gives us the y component, and mu equal to 3 gives us the z component. And so that gives us everything we need. Essentially, we could write the 3 as a 3-component vector. The Minkowski force is Q over 1 minus u over c quantity squared, the electric field plus the velocity crossed into the magnetic field. Okay, so the last thing we need to consider, and now moving into relativistic electrodynamics, is the potentials. So how are we going to write the potentials, the electric and magnetic potentials, in relativistic form? Well, if you remember that the electric field is written as the potentials of minus the gradient of the electric potential minus the time derivative of A, and the magnetic field is the curl of this potential A. So looking at something like the electric field, it gives us a hint that we're taking the spatial derivatives of one potential and the time derivative of another. So if we're combining together space and time into a single four-dimensional quantity, then maybe we can connect the potentials into a four-dimensional quantity. So we can write the 4 vector of the potentials, A mu, as V over C, AX, AY, AZ. So the 0th component of the fields is the electric potential, and the 1, 2, and 3 components are the X, Y, Z spatial components of the A vector. Okay, so since the electric and magnetic fields are derivatives of the potentials, we can now write down our field tensor, which is just a 4x4 matrix of electric and magnetic fields, as derivatives of the relativistic potentials. So we actually will write it as A nu dx mu minus A mu dx nu. And so what you should notice right away is that these terms in the denominator are covariant. So in the end, these are covariant in the denominator, which really means they're raised operators. And so this is not a dot product. Instead, it's kind of easier to see if you write this as this right here. So all the terms in this equation have raised operators. So it's not a dot product, doesn't give us a scalar value. So this is what gives us the 4x4 matrix form of the field tensor. So this, in fact, is a rank 2 tensor. Because if you were to put in all of the indices for mu and nu, you would get a 4x4 matrix. Okay, so let's just check this to see if this really works. And so if we use mu is equal to 0, nu is equal to 1, that would give us F01, which would be the derivative of A1 x0 minus the derivative of A0 x1, which if I put this in, I would get the derivative of AX with respect to CT minus the derivative A0 is V over C dx, which if I put this together gives me 1 over C, the x derivative with t minus 1 over C dv dx. Let me get my parentheses written correctly. Okay, so I factor out the 1 over C, and oh, I'm sorry, this is a minus. I thought I missed a minus sign. This is minus CT, which gives us a minus sign here, which means I can factor out a minus 1 over C, and I get dv dx plus dax dt. So this is the x component of what we wrote down before. So this is essentially EX over C, which is what that term F01 is. F01, if you look back at the field tensor matrix, is EX over C. And so if you look through them all, mu equals 0, nu equals 2, gives you EY over C, mu is equal to 0, nu is equal to 3, gives you EZ over C. And so if you use all three of those, if mu is equal to 0 and nu is 1, 2, and 3, then what you get is the electric field over C is equal to minus 1 over C dA dt plus the gradient of V. So in the end, you get the familiar equation that we've used many times before, minus the gradient of V minus dA dt. Okay, so next we can look at some other indices. So if I look at mu is equal to 1, nu is equal to 2, I would get F12, which is the derivative of A2 by x1 minus the derivative a1 by x2, which is the derivative ay dx minus the derivative ax dy, which, if I look at this, is the curl of the potential A, the z component of that, which, if I look back in the matrix for what F12 is, that is the z component of my magnetic field. So in the end, if I include now mu 2, nu 3, mu 3, nu 1, that gives us the x and y magnetic fields. So in the end, what you get is the curl of A is equal to the magnetic field, which is the other equation we used for potentials. So in the end, this works out just fine if we were to write F mu nu in terms of potentials. So we would have mu A nu minus nu A mu. So now we can don't have to write it in terms of fields, we can solve everything in terms of potentials. Okay.